this is the goal of this presentation is to describe how to find patterns in large graphs. Feel free to ask questions if necessary. We'll give short answers now and then longer answers at the end of the talk. And this is part of the Pegasus system, which is freely available, open sourced with Apache license. And this website also has code and papers. So slides with pinkish background are outline slides. So let's see the introduction and motivation. Why we should worry about graphs. I guess we're preaching to the choir here. There are huge social networks like LinkedIn, Facebook, Twitter. There are even more social networks. Let me see. Even more networks that are not necessarily involving humans. So this is a prey-predator network of species and an ecosystem, and want to figure out who is the most important species here, which if becomes extinct, the whole ecosystem will become unraveled. The one on the, this is visible, right? So the one on the bottom right is a computer network. So there are autonomous systems. Every dot is an autonomous system, like linkedin.com, cmu.edu. And there is a connection between the two autonomous systems if there is a link between them. Again, want to figure out who is the most central node, are there any patterns, any exceptions, any anomalies, right? The list continues. Traditional information retrieval also can be casted in terms of graphs. We have documents on one side, terms on the other side. Every document that contains a term, we have an edge, and this forms a bipartite graph. The web is a huge graph with sites pointing to each other with hypertext links. The list continues. Viral marketing and word-of-mouth campaigns are very important. Who is friends of whom, and therefore who can influence whom to buy our new product. Web blogs, which blog points to what blog, and which blog is the most influential one, and everybody copies ideas from that blog. It's important to find that. Computer network security, which machine sends messages, sends packets to what machine, which email account sends a message to other email accounts. Are we under attack? Do we have a port scanning situation? Do we have a distributed denial of service attack, and so on? So the first problem is how to find patterns in graphs. This is the outline. And the goal is to figure out how the internet looks like. If we plot it carelessly, this is the autonomous system graph, we see the Death Star. Every node seems to be connected to everything else. We cannot tell any pattern, right? So we would like to see how graphs look like. How does Facebook or LinkedIn graph looks like? What is normal, what is abnormal, and which patterns hold. So the observation we will repeat again and again in this presentation is the size of the data helps us find patterns. So here is a fictitious example. We have 3 points in two-dimensional space. We cannot say any pattern. We cannot say which is normal or abnormal. If we see many more points, and those points happen to be on this fictitious homemade line, then we can say that the dot that is not on the line is an anomaly. So the point is that the larger data we have, the more patterns we will discover, the more anomalies we will discover. So let's go back to graph mining. Are real graphs random? As Monica mentioned in the presentation, we know that they're not. We are all familiar with the 6 degrees of separation, the Milgram experiment, right, or the Kevin Bacon oracle, right, which actor has played in a movie with Kevin Bacon. This is one step away, and so on. There are also patterns with respect to the degree distributions and other surprising patterns that we'll describe in this presentation. So let's look at the data. So the first solution for static patterns, S1, is that the degree distribution is very skewed. This is real data, the autonomous systems. Plotted carelessly looks like a mess, the Death Star. If we plot the degree, and this is the plot pioneered by Zipf in 1949. So we have, on the vertical axis, we have the degree of every autonomous system, and on the horizontal axis, we have the rank. So AT&T has rank 1, AT&T.com has rank 1, with degree 800. IBM.com has degree 2 has rank 2 with degree 600. If we plot all the autonomous systems, 3,000 autonomous systems in this example, we see that in log-log scales they fall on a line. And the line has slope 0.8, which is the generalized Zipf distribution. If the slope was 1, that would be exactly the Zipf distribution, right? So this is surprising because people expected that everybody would have degree 3, which is the average degree, and this is not the case. The second pattern is that if we take the adjacency matrix of who is connected to whom in this autonomous system graph, and we compute the eigenvalues, and we won't go through the definition of eigenvalue, right? We load the matrix in MATLAB, we press the button, we get the top 100 eigenvalues, right? And if we plot them, the horizontal axis is the rank, the vertical axis is the value, the absolute value of the eigenvalue. So the first eigenvalue is around 40, the next is around 20, the next is around 30, whatever is the value. If we plot them, again, we see a line in log-log scales, which means a power law fits well. The slope of this line is 0.48 for this specific data set. And there was some very nice analysis by Milena Michail and Christos Faloutsos, which showed that under mild assumptions, the slope that we see here and the slope we had in the previous pattern are related. One is half of the other. The list continues of patterns. Are there similar patterns in graphs from other domains? The answer is yes. Here is a bipartite graph of users on one side, 20,000 users, who agree to put monitoring software on their computer. And here are about 100,000 sites that these users visited during a period of the experiment, about several weeks, right? So there's a bipartite graph. If we plot the in degree of the sites, everything was anonymized. So users and sites were anonymized. So the most common, the site with the most visits, let's say, was quote, quote, eBay. It was Yahoo or LinkedIn or some site like that, we don't know, right? But this site had a lot of visitors, almost everybody, 23,000 visitors visited this website, and there was only one website like that. On the other hand, there were about 100,000 websites, almost all, the vast majority of websites, they were visited only once. What is impressive is that in log-log scales, we see that the line fits well. The similar patterns we see from a data set that was studied by Matt Richardson and Pedro Domingos in KDD 2001. This is the opinions.com data set where people write comments about products and then people write comments about the comments of people, right? So here, this dot corresponds to a person who trusts 2,000 other people, 2,000 opinion users, and there is only one person like that. And here we see that there are about 20,000 people that trust only one person. In log-log scales, again, a line fits well. Maybe we can fit a parabola, but it is definitely not a Gaussian, not one of the standard textbook distributions. Very skewed, very heavy-tailed distribution. And there are many more examples. Number of sexual contacts in a paper by Lileiros and their colleagues. The income distribution follows the so-called Pareto distribution, which colloquially is described as the 80-20 distribution. 80% of the wealth goes to 20% of the people. 80% of the work is done by 20% of our employees, and so on and so forth. Duration of downloads is similarly very skewed. Experiments by Bestavros at Boston University. There are a few files which are huge files, maybe data sets or video clips. A lot of files are audio clips, and the vast majority of files are short emails, short text files. Duration of Unix job the same, CDLS, tiny little jobs that take a few seconds, less than a second. Once in a while, we have a backup who takes a few hours. Sizes of files of users. I'm sure we all have a forgotten core dump from a few years ago that is lurking there, and the vast majority of our files are very small, very short text files. There is even a book, the book of Black Swans, which says that we should not be surprised if we see huge deviations from the average. Right. So we saw patterns with respect to static graphs, degree, diameter, and eigenvalues. Let's see patterns with respect to triangles. So for social networks, what happens is that if we have this person who has two friends, sooner or later, these two friends will become friends between themselves, right? Because we are introducing our friends to each other, we throw parties and we introduce our friends. So eventually we have a lot of triangles that are closing. Now the question is, what can we say about triangles, the number of triangles or the distribution of triangles within a real social network? This is two observations, S3 and upcoming S4 by Babis Tsurakakis. This is three different data sets. So this is high energy physics theory co-authorship network, who wrote a paper with whom. So here the horizontal axis is the number of participating triangles. So the blue node here participates in two triangles, right? So what we see here is that there is one node which participates in almost 600 triangles, and there's only one node like that. And there are a lot of nodes, about 300 nodes, that participate in only one triangle. In log-log scales, a line, it has a power law tail, a parabola also fits, but it's a skewed distribution. This is an anonymous social network. We had to sign a non-disclosure agreement, so we cannot give more details. But again, the number of participating triangles seems to follow a power law. This is the opinions data set that we mentioned before, 70,000 users. Again, the number of participating triangles is not random, follows a pattern. That's the third static pattern. The fourth static pattern is that if I tell you the degree of a person in LinkedIn, on Facebook, you can guess the number of participating triangles, because the more friends you have, the more triangles there will be in your vicinity. The question is that linear? If I have twice as many friends as you, will I have twice as many triangles? It turns out that there is a strong correlation. Again, this is opinions, this is the anonymous social network, and so on. There is a correlation, but the correlation is superlinear. The slope, if I have twice the friends, I will have roughly 3 times the number of triangles, right? So the horizontal axis is the degree of a node, the vertical axis is the number of participating triangles. A line seems to fit well. The slope here is 1.7. This is surprising that the slope is about the same, 1.7 here, 1.6 here. These are 3 networks that are completely uncorrelated, right? Reuters stories, the opinions graph we saw before, a social network, anonymous social network, right? Now we're going into details, but it's very interesting how to compute the number of triangles, right? The straightforward way is do a join, figure out how many friends I have within one step, figure out how many friends I have within 2 steps, which is a 2-way join, right? And then figure out how many of the 2-step away friends are direct friends of mine, right? So this is a 3-way join. So yes, it's a few lines of SQL code to write this query, but this takes a long time. Even a plain join takes a long time. A 3-way join is even more expensive. Can we do that faster? It turns out, again, Babis came up with his observation that the number of triangles in a network, this is a theorem, is the sum of the cubes of the eigenvalues. And if we don't remember what's the definition of eigenvalues, it's what MATLAB spits out when we press the button. Yeah. But it's well defined, well understood. We don't need to dwell faster. And what is even better news is that since in most real social networks, real networks, not necessarily only social networks, the degree distribution, the eigenvalue distribution is skewed. Remember that was 6 or 7 foils ago. Then after raising it to the 3rd power, we might as well stick with the top 10 eigenvalues, because the rest won't matter anymore. There will be a 4th significant digit, right? So using this observation, we can compute the total number of triangles, and the vertical axis, the accuracy of computation, the horizontal axis, the speed up. So for the Wikipedia network, with the specifications as on the foil, we can achieve 1,000 times faster computation time by keeping the top 10 eigenvalues. And the accuracy is 94%. Notice that the vertical axis here starts from 90, because otherwise the red line would be flat. Right? So this is a huge advantage in estimation of number of triangles. How does it help us find patterns in large graphs? So this is a paper that actually fresh from the oven appeared 2 weeks ago in PAKDD 11. So if we apply this algorithm on the Twitter graph with 3 billion edges, and there was a lot of engineering that Yu Kang did to estimate the eigenvalues on Hadoop, a very tricky algorithm. What happens is that we see that, not surprises, the horizontal axis degree, the vertical axis number of triangles. So Barack Obama has a huge number of followers, right, which form a lot of triangles. Apparently, they're friends with each other, or they follow each other. More or less the same is true for John McCain, Hillary Clinton, Sarah Palin, right? Everybody's along this line, log-log scales, right? So the slope is the same. There are a lot of points here that we delete to make the plot clearer. What happens is that there is a cloud of points here which have an abnormal number, extremely high number of triangles given their degree. And closer inspection showed that these are adult advertisers, right? So this is an easy way of spotting strange abnormal patterns. Let's present the pattern of eigenspokes. So this is joint work with Aditya Prakash and colleagues from Sprint. So the problem there is how to find patterns in a who calls whom network. So we have an adjacency matrix, 1 million people calling 1 million people, right? How does this look like? And we use the the eigenvalue decomposition again. So the idea is that we're getting into details, so we can skip this part if it's getting too tricky. But the idea is to consider each one of the callers as a vector in 1 million dimensional space, right? Because it has 1 million possible targets to call, right? So we cannot draw 1 million dimensional spaces, so let's draw a two-dimensional space. So let's say that this is our caller, the red dot is our caller. The eigenvalue decomposition will find the best plane to project, in this case the best line to project, and therefore we can project our 1 million callers into a one-dimensional space in this example, or two-dimensional or three-dimensional space, a low-dimensionality space. So this is what is coming up next. So here we find the best line to project, the principal component. This is the second best line to project, the second principal component in this hard to imagine 1 million dimensional space, right? If we project our 1 million callers into this two-dimensional space, what should the plot look like? Well, we were expecting that most of the callers make few phone calls, right? Skewed distribution, most people don't make phone calls, despite what we want to believe. Therefore, there should be a lot of points here at the beginning of axis, and maybe some points here, maybe some heavy callers here, some big talkers here, right? What happened was very surprising. Yes, most of the points were at the origin, but there was a few, about 10, 20 points on the horizontal axis, almost perfectly aligned with the horizontal axis, 5, 10, 20 points on the vertical axis, and this was very surprising. We thought there was a mistake, we checked the code again, but there was no mistake. What was happening is that the same phenomenon was happening across time, was happening with almost every other eigenvector we tried. So this was the first versus the second eigenvector, third versus fourth, fifth versus sixth, first versus ninth, it didn't matter. Almost all of them, they had this spoke pattern, right? The pattern persisted across time, so we had phone calls for the month of June, eigenspokes. Month of July, similar eigenspokes, not identical, but similar. Across space, we had data from one switch, let's say Atlanta, it was not Atlanta, but let's say Atlanta, from Seattle, from any other place, more or less the same pattern was happening all along. And the same was also happening with a patent citation, which is publicly available, and we'll see data in the next few foils. So what is happening? What could be the explanation? So one sufficient but not necessary condition is that the points that we see here have the same neighborhood. One reason they would have the same neighborhood is because they like each other and they call each other, right? A second reason is that maybe they don't like each other, but they like the same friends and they call the same. So maybe it's a bipartite core. So these are two sufficient conditions. There are a few more, right? But apparently these are what is happening with our data. And let's test the hypothesis, right? So we took the 10, 15 people, 15 callers that formed the first eigenspoke, and we did the spy plot. So here is 20 people and the same 20 people, and we have a dot whenever the row called the column, right? And we see that more or less they like each other, they call each other very often. It's not a full graph, right? So standard graph algorithm for spotting clicks won't work, right? Because there are some missing dots here, but it's very dense. And the same is true for the members of the second eigenspoke, third eigenspoke, and so on and so forth, right? So what is the useful for that? This way we can spot groups with high connectivity and therefore good communities. Whether they are honest or dishonest, this is another issue, but these are groups of people that stand out. And here is, unfortunately, we couldn't get the ground truth to figure out what are these people are, but for the Sprint network. But we were able to do the same experiment for patents, and here is the most impressive eigenspoke from the patent data set, which is available from the US Patent Office, uspto.gov. So here are 100 patents, and these 20 patents are citing all the other 80 patents, and a few more, which in retrospect is not that surprising, right? If we file a patent on, let's say, superconductivity, we have to cite all the seminal patents in superconductivity. Then we file a new variation of our idea on superconductivity. Then, of course, we have to cite the same patents and so on and so forth, right? And if we do GraphViz, a visualization program, to show how these patents are forming, it looks like a spaceship. So here are all the major patents, several of the 880 patents we're citing, and here are some of the 20 patents that they're citing everything else. Let's continue with weighted graphs. So far we didn't pay attention to the weight. If I make 50 phone calls to you, this counts as one in the previous analysis. What can we say about the weights? This is work with Mary McLaughlin and Lemana Koglu. So the question is, if I tell you the degree of a node, what can you say about the weights? If I tell you I have 50 I called 50 people last month, how many phone calls did I do? Obviously more than 50, right? But exactly 50, double, triple that, what? So this is real data from the campaigns, which is publicly available. The little example here is just a fictitious example, saying that we have 3 donors here, 5 campaigns. This campaign got 2 checks. This campaign got 1 check. So the question is, if you are campaigning, right, running for office, and you have twice as many checks as me, how much more money you have? Most people will say, well, twice the checks, twice the money, right? Law of large numbers, the average price of a check is whatever. Wrong. The average price of a check doesn't exist because it follows the skewed distribution, right? Pareto distribution. The more friends you have, the higher chances one of your friends will be a millionaire or a billionaire, and the higher chances that this person will write a big check for you. So this is real data. The horizontal axis, number of checks for every campaign, right? Number of donors. And the vertical axis, total dollar amount. And we see that the slope, there is a lot of overplotting, a lot of campaigns here. But if we fit a line, then we see that the line has slope 1.16, super linear. The more checks, the even more money somebody will get. And this also allows us to spot anomalies. So here we see that most of the points are within 1 order of magnitude from the red line, from the fitting line. And we see some points like the John Kerry campaign, John Kerry presidential campaign, which had significantly more dollars than the number of checks would forecast. What about time-evolving graphs? This joint work with Yuri Leskovich when he was doing his PhD at CMU, and John Kleinberg when he was doing his sabbatical. So the question, temporal pattern number 1, what can we say about the diameter of a graph, right? If a graph grows, probably the diameter should grow. According to one theory, it should grow as log n. According to another theory, it should grow as log n. This is the preferential attachment of Barabasi. What is happening in real data? A log n is very slow, right? What is happening in real data? The answer is that both theories are wrong. The derivations are correct, but the assumptions they are using are wrong. The diameter shrinks over time. Here is one of the several data sets we tried. This is the patent citation network that we mentioned before, freely available from the US Patent Office. So at every year, we get a snapshot of the patent citation network, and we compute the diameter. The diameter is how many steps we need to go from the furthest away patent to its furthest away patent. And we see that initially the diameter is 35, but as more and more patents are getting added, eventually the diameter shrinks around 10. And this is a sizable graph, almost 3 million nodes, 16 million edges. The second pattern is what happens to the number of edges. Suppose that last year we had so many nodes in our network, so many customers of LinkedIn or our social network, and this year the number of users doubled. What can we say about the number of edges, number of friendships between them? Most people will say, well, it should double too, right? What else? It turns out that it overdoubles. And what is happening is if overdoubles in a very regular pattern. So here is the number of nodes at time t, the number of edges at time t for the US patent citation graph again. And every dot corresponds to a year. So this is 1975, the beginning of the measurements. This is 1999. We see that the slope is, a line fits reasonably well, and the slope is, sort of makes sense, is 1.16. A slope of 1 would actually, if the graph was a perfect tree, then the slope would be 1. The number of nodes would be roughly the number of edges, and that would be it, right? If the slope would be 2, or if the graph was fully connected, every pattern points to everything under the sun, then the slope would be 2. So the slope of 1.6 makes sense. It's denser than a tree, but not as dense as a click, which would be unbelievable, right? But the fascinating part is that some invisible hand keeps all the patterns citing each other on a power law. More on time-evolving graphs. This is work also with Mary and Leman. What happens to the disconnected components, right? For almost every graph we have, usually the giant connect component is 99.9% of the graph, so we ignore the disconnect components because we don't know how to handle several mathematical properties. But the question is, okay, let's look at the second largest connect component and so on. How should they grow? How should they change over time? So one theory would say, well, everything should grow proportionally, self-similarity, fractals, and things like that. So if the giant connecting component grows, the second largest connect component should also grow a little bit, and the third and the fourth, right? The other observation says yes and no, right? Because if a new pattern comes in and points to one patent, or a new friend comes in and makes friends with somebody from the giant connect component and from the second largest connect component, the second largest connect component is absorbed in the giant connect component, and therefore disappears, right? So maybe the size should shrink, and then eventually everything will be absorbed in the giant connect component. The third argument would be maybe things will stabilize, right? So what is correct? It turns out that all three are partially correct. What is happening, this is IMDb, Internet Movie Database. This is the bipartite graph of movies and actors, who played in what movie. The horizontal axis is time, the vertical axis is the size of the connected component. We don't plot the giant connected component because it would be way off scale, it would be somewhere there, right? So we plot the second largest connected component in blue and the third in green. And we see that all three previous theories are sort of correct, right? The second connect component grows until it gets absorbed, and then grows again and gets absorbed, and so on and so forth. And magically, they seem to sort of stabilize, or oscillate within a fixed boundaries. What about more temporal patterns? What about timings for blogs? Now the question, temporal pattern number 4. Suppose I have the red box is my blog, and at time t I write a blog posting, right? The red solid circle, saying expressing some opinion. And then this is your blog, and sometime later you write another posting which agrees or disagrees with my opinion, right? Now the question is, what is the distribution, the PDF of the lag? Most probably, we would expect that most of the reactions will happen within a day. After 2 days, there won't be too many reactions, right? After 3 days, the issue will have been forgotten, right? So how would this curve look like? Probably dropping off exponentially, right? Human memory sort of is modeled as exponential drop. Is exponential correct? It turns out that it's not. The horizontal axis is the logarithm of the lag. The vertical axis, the logarithm of the links. This is adjusted for weekends. And we see that the line fits well. There is a knee at 40 days, which is probably due to horizon effect. The data set was 60 days long. So the question now is, okay, this a line sort of fits well. What should be the slope of this line? The most natural slope is -1, right? Zip distribution and all that. It turns out that it's not 1, it's 1.6, which is very close to the -1.5 of the Barabasi stack model. The stack models is a very simple and ingenious way of describing how humans do tasks. So the idea is we have a task, a list of things to do. So we pick the first thing from the list and says, go shopping. Okay, we go shopping, get our groceries, and then put the card in the middle, somewhere randomly in the middle of the stack. And then we take the next card, which says, write a paper, right? And then we write the paper, and then we write. So how often are we going to do shopping? It turns out that the time intervals between shopping events follows a power law with slope 1.5 in this example, which is tantalizing because the zero crossings of a random walk also follow a power law with minus 1.5 exponent. This is a theorem from random walk from Feller. So the plot here is the horizontal axis time, the vertical axis the capital of a gambler in a fair casino, right? They flip a coin, you get $1 or you lose $1. How often are you going to break even, or what is the time between break-even events? This time is not Poisson, is not any other thing, any other we have seen in standard textbooks. It is a power law with slope 1.5. What is even more fascinating is that the response time of males from Darwin and a few centuries later from Einstein, they also follow a power law with exponent minus 1.5. So most of the males, Einstein answered within a day, a few of them within 2 days. There was, and it was dropping off, and there was one which he answered after 30 years, or something like that, 10 to the 4. So power laws with, and this slope seems to have some very interesting properties. Temporal pattern number 5, what can we say about the duration of phone calls? This is joint work with Pedro Vaz de Melo. So the question is, we have a phone call network, we know who called whom. Let's focus on one of the most talkative people and figure out what is the duration of this person's phone calls. Let's call him Smith. It was anonymized, so let's call him Smith. So what was the duration of his phone calls? So we would expect probably a power law. The duration for 1 second, there should be a lot of phone calls, oh mistake, sorry, click, right? 2 seconds, maybe fewer, 100 seconds, maybe even fewer, right? That's our guess, right? What would reality look like? It turns out that the reality is much more complicated than that. It looks like a parabola with some deviations here at the beginning, right? So blue dots are the data. The black line, the black dashed line is the exponential. We didn't expect exponential or Poisson is completely discredited, right? But we plot it anyway just to show that it doesn't hold. Log normal is the green line, which fits this part but not the rest. The TLAC distribution, which we'll describe next, is based on the log logistic distribution, which seems to match much better than the previous other distributions. So let's see more details about this TLAC distribution and the log logistic it is based on. This distribution says that, intuitively says that the longer a task has taken, the longer it will take in the future, right? So suppose we have we want to build a house, we hire a contractor, the typical time to build a house is 1 year. After 5 years, suppose that the house is not built yet, how long it will take to be built? The exponential distribution will say, well, 1 year, right, memoryless. This distribution says, if it took 5 years, the contractor is probably in jail because he was unethical, right? So probably your house will never be built or will take 50 years to be built, right? And this is the idea behind the truncated lazy contractor distribution, which is also based on the log logistic distribution. This distribution has been used in survivability analysis. So suppose, knock on wood, we have a disease. We are medical doctors studying a disease, right? So the odds ratio at time X is how many patients died before within X years from the diagnosis versus how many patients survive after X years from the diagnosis, right? So if we plot this ratio in logarithmic scales and the horizontal axis, the age, the duration, then for several diseases, this follows a line, and this is exactly the log logistic distribution. For the phone calls of the anonymous Smith that we mentioned just a second ago, this is real data, the blue dots are real data. Again, a line fits well. So there is a power law, there seems to be a power law between the odds ratio of the phone calls and the duration. And we did experiments from a large phone call data set from a city in Asia, 4 months worth of data, 3 million users, 1 billion phone records. We kept only people who made at least 30 phone calls because otherwise we cannot do any serious fitting. And 96% of these people would follow, in their phone calls, they would follow the truncated log, the TLAC distribution. The ones that didn't had very strange behavior. They had too many phone calls which were exactly 1,000 seconds long, abnormally high. Probably there was some faulty switch or there was some pricing scheme that you would not pay, you would get free phone calls if you would stay less than 1,000 seconds. So these were the only violations. Let's continue on problem number 2. Now that we know what patterns to expect, how can we put them to use? How can we find anomalies? So let's see the oddball project, again with Leman and Mary. So the idea is we're given a big graph, which nodes are strange, which nodes we should suspect and look further into them. How do we proceed? Well, let's look at the neighborhood of every node, the one-step away egonet, extract some features, number of edges, total weight, total number of phone calls, and so on, and see whether this person or computer or whatever the node is deviates from the rest of the population. So what is the one-step away egonet? Let's say the egonet for node V3 is everybody who is one step away plus all the induced edges between them. So this is the egonet of node V3. The egonet of node V1 is, again, everybody one step away, all the induced edges, the induced subgraph. So this is the egonet of node V1. Okay, so now for every node we can extract the egonet. The question is, how can we characterize a whole graph, squeeze it into a few numbers? What would be these good features to extract? We tried about 12 features. Of course, the number of features is infinite, right? We tried 12, 13 features. We'll present 2 or 3 of them. So the number of neighbors makes a lot of sense. The number of edges in the egonet, which roughly corresponds to the number of triangles. The total weight in the egonet is also a good feature, the first eigenvalue, and 8 more features. Let's see the results, which are very easier to explain. So let's have 2 of the features, the number of nodes, the number of nodes in the egonet, and the number of edges in the egonet. So this is a postnet, blogs pointing to each other, blog postings pointing to each other. Every dot corresponds to a blog. And we see that most of the blogs are along a line of slope 1, which means they sort of form a tree. If we look at the furthest away dot here, this corresponds to instapandit.com, which is a conservative blog. And if we look at its vicinity, well, it's hard to see it because it has a lot of friends, but it looks like a star. There are some of the people that follow this blog, that point to this blog, are friends between themselves. They are pointing to each other, but mainly it's a star. So this line, not surprisingly, with slope 1 corresponds to star-like egonets. Contrary to that, the blue line corresponds to nodes. It has a slope of 2 and corresponds to nodes whose egonet is more or less a perfect clique. And if we look at the most populous one, this is Sizemore at UK, we see that it's more or less a very nice clique. Apparently, this person or persons, they created a website that they were writing comments for movies, and apparently they created multiple websites pointing to each other. Otherwise, it's hard to explain this situation. Let's see an application of oddball on the Enron data set. This was emails during the Enron scandal that was, and all these emails were confiscated by the federal government. So now for every email account, corresponds to a dot, and we can try to, and we plot the number of nodes in the egonet and the number of edges in the egonet. So we see that most of the people have a slope of 1.3, which means they are not exactly trees, they are not exactly cliques, they're somewhere in between, which makes sense. This is probably typical human behavior, right? Some friends they know each other. The ones that are on the slope 1, they correspond to trees, actually not even trees, stars, because we have only one step away. And the most populous tree corresponds to Kenneth Lay, the deceased CEO of Enron, which apparently the people he mailed, they didn't know each other, or they had very, very few friendships between each other. And the same is true for the remaining nodes on the slope 1 line. This is also a director. Andrew Lewis was also a director, and most of the other people on the slope 1 line were directors and apparently sending messages to subordinates that they didn't know each other. Let's skip this part. Actually, no, let's continue this part. So, eBay fraud detection. This is joint work with Polo Chow and Shashank Pandit. So the question is, We have sellers on eBay, sellers and buyers. Every node corresponds to a human. Every edge corresponds to positive feedback, because on eBay almost all feedbacks are positive. Negative feedback is very painful for both sides, right? The one side that gets a feedback is mad and retaliates, and so all feedbacks are positive. So the question is, we want to buy, this person is trying to sell something. Would we trust this person? This person has 1, 2, 3, 4, 5 positive feedbacks. So looks sort of trustworthy, right? This person looks not as trustworthy, right? It has only 2 feedbacks. So what can we say about these 2 people? It turns out that the top people are dangerous. The bottom people in green are probably honest. And the middle people are part of an extremely ingenious scheme. So what the yellow people are doing, let's call them accomplices, they never do anything bad. They stay on eBay for years. What they're doing is they're buying and selling low price elements from honest people, so they build a good reputation. The only bad thing they're doing is that they give very good feedback. They give feedback to bad people who are ready to commit fraud. Probably this is the very same person who creates all these accounts, right, and logins. So what happens is that somebody might say, oh, this person, backtrack, right? This person looks pretty honest, right? 5 positive feedbacks. So I'll send a $3,000 check and hopefully a laptop will come soon, right? That laptop never comes, right? And this account is deleted after a week, but the criminals, they don't have to sweat it, right? If this account dies, then this person creates another account, gets excellent feedback from his own self, right, from his accomplice accounts, and then the scheme is ready to fire again, right? So what is a telltale sign is that this is a near bipartite core. Almost all of the accomplices give good score to almost all of the dishonest people. And this way, with belief propagation, we won't go into the details, but with belief propagation, we can spot these bipartite cores and warn people or take measures. So that attracted a lot of positive publicity. It even attracted less desirable attention. We even got a message from somebody claimed he's from the Belgian police, and he wanted a copy of our code, apparently to reverse engineer what we were doing. My colleague said that don't reply. The Belgium people from Belgium or people that claim are from Belgium are not to be trusted with respect to eBay. Yeah, I'm sure people from Belgium are very honest, but apparently somebody's hijacking their good fame. The next part is immunization, so we have a little bit of time. So we have a network which knows to immunize, which will a virus take over or not, or will it create an epidemic? So the problem is very clear. We have a network. We have K vaccines, 2 vaccines in this case. We know the virus detail, what is the chance that the virus will propagate through a sneeze or a handshake, and how long the person will stay sick. And the goal is immunize the nodes so that we make the life of virus as hard as possible, right? To protect our population as much as possible. So the goal is we want to immunize, the main idea is we want to immunize the nodes that will maximally raise the so-called epidemic threshold. The epidemic threshold is the virus, the threshold below which a virus has no chance to survive. A quick introduction to immunology terminology, right? A flu-like virus has no immunity, right? We get sick again and again, right? This is called the SIS model, susceptible, infected, susceptible. Lifetime immunity is the SIR model, like mumps, and there is temporal immunity, right? Finite length immunity, and so on. Beta is the probability that a virus will propagate through a sneeze. Delta is the probability that a host will recover within the next time tick. So the question is, if we are given a network, what can we say about the epidemic threshold? Will a virus take over? If we know the beta and delta of the virus, will a virus take over or will it become extinct? And the epidemic threshold depends on the connectivity, right? If we have, in this example, we have 4 people who are not connected, let's say 4 monks which have vowed silence. We tell a rumor to the first monk, and of course after a while the monk forgets and the virus dies out, right? So this is the worst case scenario for the virus, the best case for us. Here the virus has better, the virus or rumor or product we want to market has better chances. Here it has even better chances, despite the fact that they both have 3 edges, right? This is better for the virus because this is the kindergarten situation. We send our kids to kindergarten, they get all germs, and then we're all sick throughout the winter, right? So the more edges, the better for the virus. The higher degree, the better for the virus. Some analysis showed that the variance of the degree also influences the setting. What else? How many parameters do we need to study the threshold? It turns out that the threshold depends on only one parameter, the first eigenvalue of the adjacency matrix. It's a long story. We have very elaborate proofs. This is true not only for the SIS virus, for the flu virus, but Aditya Prakash, we showed his photograph before, was able to show that this is the threshold for almost any model of virus that has appeared in the literature. Flu, mumps, pertussis, HIV virus, anything. The only thing that matters from the network is the eigenvalue. And we're discussing that maybe this can help us study how quickly will a new idea or a new product will go over a network. Here are arithmetic examples. We infect a small proportion of a network, and when we're above the threshold, then the number of infected people sort of stabilizes. It doesn't infect everybody in the network, right? But a lot of them. If we're below threshold, the number of infected people dies out, and this is it. The last part is scalability. We don't need to talk about scalability, why scalability is important and why Hadoop is important. But let me go over quickly about the diameter. We implemented a diameter estimation algorithm on Hadoop. The algorithm is, the straightforward algorithm is tricky because it requires n square space and at worst n cube time, so it's awful for if the number of nodes is 1 billion. But with careful engineering and approximations, we can make the algorithm proportional to the number of edges. Let's see the results instead of going through the details. So the results, the horizontal axis here is the radius of every node, and the vertical axis is the count. How many nodes of the graph have radius 0, 1, 2, 3. So 13 years ago, Barabasi studied a small part of the web, 1 million nodes, for a crawl from Notre Dame, and found in a milestone paper, found that the diameter was 19. So with 19 hops, everybody can reach everybody else. This was impressive. It's still impressive, right? Now the question is, now that we have a graph, and we're thankful to Yahoo, who gave out this graph, 1.4 billion nodes, 6 billion edges. What happens to the diameter in this case? Well, it's 1,000 times bigger, so probably the diameter should grow. Oh, wait a minute. 20 foils ago, we saw that the diameter shrinks. So what happened? Grow or shrink? It turns out that it shrunk. And the diameter is 14 for the directed graph, 7 for the undirected graph, which is tantalizing because this is very close to the 6 degrees of separation of Milgram, right? 300 people from Milgram, 1 billion node here, with the numbers 6 and 7 still kick in. So we're not done yet. Now that we have this Hadi algorithm from UConn, we can not only figure out the diameter, we can also figure out how is the radius plot, right? So we expect that most of the nodes will have radius roughly the diameter, 7, right? That would make sense. What about the rest of the distribution? Would it look like a Gaussian distribution? It couldn't be Gaussian because we cannot have negative diameters, right? Negative radius. So maybe it's a tilting Gaussian. The reality defied all our expectations, so this is how reality looks like. So there are a lot of nodes with with radius 0, which means they are completely disassociated. They don't point to anything. Nobody points to them. A lot of nodes have degree 1, radius 1, radius 2, and so on and so forth. Then there is a spike at 7, not surprise here. Then there is a mini spike at 15, another mini spike at 20-something, 23, and a slow drop. This is probably the only plot that is not log-log. This is linear, and the vertical axis is logarithmic, right? So what is happening? All the 0, 1, 2, 3 radius nodes are from disconnected components. So if we only study the giant connect component, all the left part goes away. Google stands out, is the only node in this snapshot that has radius 5, and everybody else has 6, 7, and more. How can we explain the multimodality? Why do we have little spikes here? We don't know, but maybe what is happening is we have the English-speaking part of the web with diameter roughly 7, the German-speaking part of the web with more or less diameter 7 again. Remember, the size doesn't really matter. The degree, the radius is 7, no matter how large the network. Maybe the Portuguese-speaking part of the web, Brazilian, right? And they are sort of, maybe they are connected like that, which creates these little spikes at 7, 15, and so on. This is a conjecture, we need to study it, right? Let's keep that part. Connected components, let's see, we are running out of time, but let me go quickly over the connected components. This is also work with Babis Tsurakakis and Yukang. So the idea here is that if we take the connect components of the web graph, the horizontal axis is size of the connect component, the vertical axis is count. So not surprising, the giant connect component is humongous, right? We have 1.4 billion nodes. We see that almost all of them are in the giant connect component. Okay, that's not surprise. But the second observation is a surprise. We have almost half a billion nodes completely disconnected, completely isolated from everything, right? The third observation is even more surprise. The remaining, the size of the remaining connect components seem to follow a power law, or at least a line sort of fits well. And the fourth observation is that there are little spikes which deserve further attention, right? So there are, here is at size 1,100, and there are 65 disconnected components. We have exactly this size, too much of a coincidence. Further inspection showed that these websites are financial advice websites, probably phishing, PH phishing websites. They don't exist right now. Or there were other suspicious sites, probably created by a cookie cutter situation. I was an unscrupulous web designer, right? Here is a ready-made site to scam people. Here is a copy for you, here is a copy for you, here is a copy for you. 1,000 copies, like 65 copies like that, right? This is data from LinkedIn, which this is 2003, 2004, 2005, 2006. The same axis, we see that, again, the same observation, the giant connect component has taken off. A lot of disconnected nodes, and the slope is 2.5, 2.7 for all 3 years, which is fascinating. And it's even more fascinating because the graph grew by almost tenfold. It doesn't show in logarithmic scales, but this is 1 million, and this is 10 million here. So it's not that the graph stayed the same. It 10 times bigger size. And we are done. The low-level conclusions is that we saw several patterns, the fortification pattern, the shrinking diameter, the triangle laws, and so on. We saw new tools, the oddball tool and the belief propagation, and so on. Scalability is an important issue. And the high-level comment is that large data sets will show us patterns that we didn't even expect and that are not visible in small data sets. These are the citations, and credit where credit is due. Right? This is the team, and these are the funding agencies. And that's the end of the presentation. Thank you.
Thank you, Christos. And we'll take a few questions now. Please use the walk-up mic if you'd like to ask questions. Sure, I'll be the mic runner.
I'll repeat the question if necessary.
Just to go back to the eigenvector and eigenvalue analysis of these static graphs, you had only looked at the top 10 eigenvalues and corresponding eigenvectors, and of course they're going to be perpendicular, I mean, by definition.
Right.
So the real question is, when you start breaking them down past, say, the first 100, can you actually order them through simple cosine, and is it an even distribution, or do they cluster? Did you even look at that? Of the eigenvectors beyond, say, the first 100 or 200, was there an even distribution across the full vector space, or did it just actually cluster? Because that would be more interesting, and did it match up then to eigenvalues that you saw?
Let me see if I understand the question. So the vectors of the eigenvalue analysis are vertical, perpendicular by definition, right? How the actual data points fall in this two-dimensional space is anybody's bet, right? They don't have to be aligned with axes, right? So this is not something that is expected, right? or at least it was not expected by us.
Okay.
Right?
If to me it seems obvious. I mean,
It's obvious. Okay,
by
let's
definition.
try another data set and see if it's if it happens there too.
But if you've got your eigenvectors and by quote unquote ordering them and you take the top 10, they should be independent. Thus, if you look at the data in the eigenspace, the two-dimensional space of your two eigenvectors, they should be perpendicular. They should run across the two axes.
Okay, let's take it offline because I don't think it's obvious.
But they've taken it as basis.
Yeah, so the plots, yeah. So this is what, so yes, the first U1 vector and the U2 vector will be orthogonal, but it's not clear that the data points will be aligned with axes, right? And let's take any other data set, and actually for all other data sets and for principal component analysis, the expectation is that these points will follow a multivariate Gaussian and actually a nice multivariate Gaussian, a nice circle, right? The whitening transformation. Let's take it offline, yeah? But it's not obvious at all. It's not expected. I'm surprised you expected it. Next question.
Okay, do you think any difference between the social networks and the networks you mentioned here? Because I believe many people here in this room they are interested in the social networks.
Oh, very good question. So whether there's any difference between social networks and other networks like prey-predator networks or computer networks? Good question. I don't know. We have to check, right? My guess is social networks will probably have more triangles. Computer networks, maybe they have triangles if the owners of the workstations are friends and they send messages to each other, right? So the short answer is I don't know. That's a very good question, but we are developing the tools to help us distinguish, right? So we can plot the number of triangles versus number of edges for the social network, for a computer network, for a road network, and see whether they have different behavior. Very good point, thanks. Yes?
We're streaming and recording, so this is a...
Okay, I'll go back to my base.
At Salis, one of these papers, he defined it kind of Bernoulli, Pascal triangle or Bernoulli experiments. And if you assume that there is some non-extensive entropy, meaning you have, they're not really independent events, then what you get is the distribution which follows the edges of the cube. So the distribution they get is actually non-uniform in the cube like you would expect, but it closely, it's similar to what you got in the one of the slides. It's a Salis non-extensive statistics. There are plenty of references on the web.
About
Salis.
Can you repeat the question? So the question is,
what is your comment? What can you comment on the connection
between what?
Between non-extensive entropy studies and
non-extensive entropy studies.
Yeah.
I know what is entropy. I don't know what is non-extensive entropy. So, so maybe we can discuss it offline. Yeah, thank you for the citation. Yeah, that would be nice.
Okay. You have a question?
Christos, can you characterize the graphs that fit better a quadratic law on a log-log scale as opposed to a linear
as opposed to a linear law?
That's
That's actually a very good question, and it's very tricky, right? So there were people in computer networks. So the answer is no, not easily. Not as easy as it looks like, right? So the question is, can we separate linear fitting, power law with a linear fitting versus a log normal fitting versus a log logistic fitting, right? It should be easy, but it's not. So there were people in computer networks that they say, okay, we have the real data, let's let's do the chi-square test with a parabola, let's do the chi-square test with a line. Both tests said yes. Right, so for their specific data set. So because exactly there are huge values that, right, all this black swan phenomenon, confuses the statistics. So it's not easy to do a good fit. But the important point is that all this what is important is not whether it's exactly a power law or a log normal or log logistic. What is important is that it's not a Gaussian distribution that everybody expects. And even worse, these distributions have infinite variance, and the central limit theorem does not hold. So if we say on the average we expect to see blah, there's no average. The average, the more people you sample, the bigger the average salary becomes, because we have a Pareto distribution salaries. The more nodes you sample, the bigger the average degree looks like. So the average is useless, and this is the major message from all these skewed distributions, that average, Gaussian distributions, Poisson distributions don't hold. So our statistics, whatever we learn in the standard statistics, does not hold anymore. Not only does not hold, but leads us to bad assumptions.
You can use the walk-up mic, please.
This may have been there in your talk, but I was just wondering if the fact that you don't see the same behavior at different scales tells us that these networks are not fractal. I mean, you didn't talk about the fractal nature of these networks at all.
Mm-hmm. We didn't talk about that.
No, we didn't. But and I don't know if there's any reason to do so. But the fact that at larger scales, as you yourself pointed out at the very end, that when your data set tends to become large, it shows different behavior from when it is small. So is that telling us something about the non-fractal nature about these networks?
What I said is that if we have a large data set, we'll see phenomena that we didn't see before. They were hidden, right? If we have a social network of 20 people, we'll never see the power law distribution, power law, log normal, whatever distribution, right? And statisticians, right? So if we have 1 billion nodes, we'll see other phenomena that were hidden with a small data set. And I think we are in a unique position in this decade to study huge graphs and learn about human behavior and computer behavior that we were not able to study before. Whether they're fractal or not, it's yeah, we can speculate about it, whether the real networks are self-similar or not. We had the Kronecker generator, which is exactly self-similar, right, and gives reasonably realistic graphs, right? We can discuss it offline if you want. Yeah, good question. Thanks.
Hi, I had a question about the eigenvalue solver.
Yes.
So are you computing exact eigenvalues? And for how long would it take to solve, I guess, the eigendecomposition for the adjacency matrix or something like Yahoo Web that's like at the petabyte scale?
Yes, yes, yes. A very good question. So we are using the Langsos method with restarts. And this is linear on the number of edges. So as you know, Langsos requires sparse matrix vector multiplication multiple times, right? Depending on the accuracy, of course, we only ask for the top 10, top 20 eigenvectors, right? And eigenvalues. This probably takes for 1 billion nodes and 6 billion edges, takes probably a few days on the Yahoo Web graph. On the M45 of Yahoo, 1,000 machines, we're using, I think, 100 nodes of this graph. So yeah, it's an expensive operation, but it's a big graph on the other hand, right?
Hi, did you guys do any work on what causes some social networks to really explode and grow versus some others? Like, for example, LinkedIn, Facebook, they've taken off really hugely, but some others which started before them, like Hi-Fi or whatnot, they've not become so big. So like, are there any characteristics that you have studied that can talk about what causes a social network to really exponentially grow?
Right, very good question. So from the structural point of view, if we're given snapshots of a network, Mary McLaughlin that I mentioned before, in her dissertation, she studied Usenet networks. And if I remember correctly, what she found is that if there are not too many interactions between the people, the group members of the Usenet, then eventually it dies out, which in retrospect sort of makes sense. Whether we can forecast whether a network will take off, I guess studying the number of interactions would be a good indicator, right?
But studying interactions would be post having members and interacting among themselves, right?
Uh-huh.
But if someone's, so let's say you're part of a social network and you invite somebody else who's not yet a part of the network, right?
Okay.
Are you calling that also as an interaction, or are you not? Because that's really bringing somebody in new into the network.
So for this type of invitations, we haven't done any study because data is hard to come by, right? Even the data we got, we had to sign non-disclosure agreements for almost half of the data set. That's a very interesting problem. Yeah, if there are publicly available data we could study, that would be great, or would be happy to sign non-disclosure agreements if you're willing to if your company is willing to give us data. Yeah.
Okay, thanks a lot. Let's thank the speaker again, and enjoy the refreshments.